Welcome to the video lecture on arc length and surfaces of revolution. In this section, we use definite integrals to find the length of an arc and to find the surface area of a solid of revolution. In order to find these, we're going to need the distance formula. So let's recall what the distance formula says. It says given 2 points, P1, x1, y1, and P2, x2, y2, the distance between the points is given by the formula d equals the square root of the difference in the x's squared plus the difference in the y's squared. And this just comes from the Pythagorean theorem. Now, in order to ensure that a curve has finite arc length, the function representing that curve must have a continuous first derivative. Such a curve is called rectifiable. And if f prime of x is continuous, that will guarantee that the graph of f of x is continuous and is smooth with no corners or cusps. So what we're going to do is we're going to take our curve and we want to partition it from our interval a to b. So a might be somewhere over here and b might be somewhere over here, and we're going to partition it however you choose. So I'm going to let x sub 0 equal to a and x sub n is equal to b, and then my x sub 1, x sub 2, and so forth would be my partitions. So you might have something like this. Now what we're going to do with this is we're going to take a look at the length of the curve between your two endpoints on each subinterval. So for example, if this is x sub 0 and x sub 1, then the length of the line segment connecting the left endpoint and the right endpoint, we can find that arc length, that little line segment distance, by using our distance formula. The two x's would be x1 and x0. So if we find this horizontal distance by subtracting x1 minus x0, that would be our little delta x sub 1, if you will. And then the two y's are y sub 1 and y sub 0. So if I subtract these two y's, that's going to find this vertical height right here, which I'll call delta y sub 1. And using our distance formula, we can come up with the distance between these two endpoints. In general, I'm going to let delta x sub I be the right endpoint x sub I minus the left endpoint x sub I minus 1. And I'm going to let delta y sub I be the difference in the y's, taking the right endpoint y sub I and subtracting the left endpoint y sub I minus 1. So here's what it's going to look like. To get the arc length of the entire curve, we're going to find the distances approximated using that distance formula for each of our line segments. So if we look back at our picture here for a moment, we're going to find this little line segment distance, then this little line segment distance, then this line segment, this distance, and so forth, all the way to the end. And then we're going to add up each of those distances, and that should give us an approximation to the entire arc length. And each of those distance formulas on each of our subintervals would look like this formula right here. So our arc length S is approximately the distance between x sub 0 and x sub 1 and y sub 0 and y sub 1. So that's that very first little line segment plus the second line segment plus the third plus the fourth all the way up to the last one. If we use summation notation to make this sum look a little bit neater, then this becomes the sum from 1 to n of the square root of x sub I minus x sub I minus 1 quantity squared plus y sub I minus y sub I minus 1 quantity squared. And that's that distance formula between our two endpoints. And we're doing this for each of our n subintervals. Okay, so now what we're going to do is I'm just going to do a little change in notation here. I'm going to change that x sub I minus x sub I minus 1 into that delta x sub I notation. So this difference right here, I'm going to call that delta x sub I, and that's being squared. And this difference right here, I'm going to call that delta y sub I quantity squared. And now what I'm going to do is I'm going to manipulate this a little bit. I'm going to multiply this by a fancy version of 1. So what I'm going to do is I'm going to multiply inside of that square root by delta x sub I squared over delta x sub I squared, which is really just 1. So I'm not changing the problem at all. I'm just putting it in a different form. So if I multiply inside of this square root by this fancy version of 1, then what we're going to see over here is I'm going to leave this first term the way it is, and I'm just going to multiply this second term right here by this fancy version of 1. And when I do that, I'm going to group it just like this. I'm going to put the delta x sub I quantity squared that I'm multiplying by on the bottom under the delta y sub I, and I'm going to put the one I'm multiplying by on the top right on the side. So this cancels out, which makes it equivalent to what we had up above. I'm just putting it in a different form. Now the reason I'm going to put it in this form is now this term right here is the same as this term right here. So I can factor that out. So I'm going to factor out my delta x sub I quantity squared. So this is going to turn into, when I factor it out of this term, this just goes to 1. When I factor it out of this whole term, I'm just left with this quotient. And the term that I'm factoring out, I'm going to put it over here. It's still underneath a square root. I just pulled it out. Okay? So all of this is what's left times that sort of GCF that I factored out. Now what is the square root of delta x squared? Well, this just reduces to a delta x sub I. The square root and the square cancel each other out. So this is going to become the sum from 1 to n of the square root of 1 plus delta y sub I over delta x sub I quantity squared times a delta x sub I. Now so far this sum that we just created here is just an approximation to the arc length by taking the small little distance formula lengths for each of my subintervals and adding them all up. Now how do I turn that approximation into the actual arc length? Well, that requires a limit. So I'm going to need to take a limit here. And it depends on our partition. If we're using a Riemann sum type of partition, then you need to ensure that the greatest partition has a length that's going to 0. We call that the norm. So the norm needs to go to 0. If this is a regular partition where each of your subintervals has an equal width, then saying that the norm goes to 0 is the same as saying letting n go to infinity, so that these subintervals get smaller and smaller and smaller, and the number of them goes to infinity. And what happens when we take this limit is it turns into our integral. We can also say by the mean value theorem, since we have a nice continuous differentiable function, that there has to be some point c sub I where the derivative at c sub I is equal to this slope of the secant line, which is our delta y sub I over delta x sub I. So by the mean value theorem, this quotient right here turns into a derivative at some point inside of that subinterval. So this becomes the square root of 1 plus f prime of c sub I quantity squared times that delta x sub I, and as we take that limit, this turns into our integral. So the summation becomes the integral from a to b, the endpoints of our original partition, and then this becomes square root of 1 plus f prime of x quantity squared, so that turns into that right here, and the delta x sub I on the end turns into our dx. So this is called the arc length of our function f on the interval a to b. So here's our formula. The arc length of a rectifiable function y equals f of x between the points a comma c and b comma d is given by the integral from a to b of the square root of 1 plus f prime of x squared dx, or if your function is not given as y in terms of x, but rather given as x in terms of y, then you can do a dy integral. So the arc length in that case would be the integral from c to d, and notice here c and d are your y bounds, times the square root of 1 plus g prime of y quantity squared dy. So you can do a dx integral or a dy integral depending on how your function is given to you. Now I will warn you that arc length integrals tend to be tough ones to solve. So a lot of times you're asked just to set up the integral because oftentimes they're too difficult for us to actually integrate. But we're going to look at a few that are able to be manipulated so that they can be integrated. So, first example, find the length of the curve, so that means arc length, given by the function y equals x to the 2/3 from 8, 4 to 27, 9. So since this is given as y as a function of x, I'm going to use a dx integral according to this formula right here. And in order to use this formula, I'm going to need to know what f prime of x is. So let's go ahead and find that first. So f prime of x, or the derivative of this function, using my power rule, I bring down the 2/3, and when I subtract 1 from the power, the new power becomes a negative 1/3. So that's going to go right here where this f prime of x is. So my integral becomes the integral from the first x to the second x, so from 8 to 27, times the square root of 1 plus 2/3 x to the negative 1/3, there's my derivative, squared dx. Okay, so now that we have our integral, we're going to need to try and solve it. So let's simplify it a little bit. We have a square in there, so let's go ahead and square this. We're going to get a 4/9, and remember, a power to a power, you multiply these powers. So this becomes x to the negative 2/3 dx. Now rewriting that as a fraction, this becomes 1 plus 4/9, and I'm going to move that x to the 2/3 down to the denominator. Now in order to make this something I can integrate, I'm going to go ahead and get a common denominator. So I'm going to rewrite this as 9x to the 2/3 in the bottom, and 1 would be the same as 9x to the 2/3 over 9x to the 2/3. So there's my common denominator for the 1, plus my 4 that I had on top over this denominator already. Okay, now notice the square root of 9 becomes 3, and the square root of x to the 2/3, that's a perfect square. The square and the square root cancel out, so that denominator is actually going to reduce nicely into a 3, and the square root of x to the 2/3 is just x to the 1/3. We lose the square on top. Alright, so this is what we have so far. It looks very messy, and it doesn't look like it's likely to be something we can integrate, but in order to do something here, we're probably going to want to try a U-substitution. Because it's so messy and it has that radical in it, I'm going to be tempted to let my u be this expression underneath that square root. So let's let u be this 9x to the 2/3 plus 4. So now we need to know what our du is going to be. So the derivative of the left side is just du. On the right side, when I bring down that 2/3, 9 times 2/3 is 18/3. And when I subtract 1 from the power, this becomes a negative 1/3 power, and I'm going to have that dx on the right hand side. Now you can do this several different ways, but I'm going to suggest here that we don't reduce this 18/3 into a 6. You certainly can, but I'm going to leave that 18 where it is, and I'm going to make that x to the 1/3 join the 3 that's in the bottom. Now the reason I'm going to do that is because this piece right here is exactly what I have already in my integral. So if I divide by 18, then 1 over 3x to the 1/3 dx is exactly this, so this is going to get replaced by du over 18. So that means this integral becomes square root of u, that's my numerator, and the dx over 3x to the 1/3 becomes du over 18. I'm going to leave my bounds off for now because these are x bounds, not u bounds. You could turn them into u bounds if you like. That's up to you. Now this 18 that's in the bottom, let's go ahead and pull that out, and it's in the bottom, so it's a 1/18, and square root of u is just u to the 1/2. So I can integrate that, and it's going to turn into a 1/18, and then u to the 1/2. When I add 1 to that power, it becomes a 3/2 times 2/3. And now I will simplify here. I'm going to get a 1/27 u to the 3/2, and now I'm ready to substitute back in terms of x. So this is 1/27 times 9x to the 2/3 plus 4, since that was what my u was, all raised to the 3/2. And then I'm going to plug in my bounds. When I plug in the 27, I'm going to get 9 times 27 to the 2/3, which actually does reduce because the cube root of 27 is 3, and 3 squared is 9. 9 times 9 is 81. And then there's that plus 4 on the side. Actually, let me go ahead and put that in here. I'll write it like that for now, and we want to raise all of that to the 3/2. So this would be 81 plus 4 is 85, so this is going to be 85 to the 3/2, which does not reduce nicely. It's going to be some decimal. And then if I plug in my 8, then this would be 9 times 8 to the 2/3 plus 4, all raised to the 3/2. The cube root of 8 is 2. 2 squared is 4. 4 times 9 is 36. 36 plus 4 is 40, so this will be 40 to the 3/2. So at this point you would use your calculator, punch these two guys in, subtract them, divide by 27, and it's approximately 19.65. Okay? So these arc length integrals tend to be messy ones. Usually I'm only going to give you ones that are solvable, typically by a U-substitution of some sort. Okay, let's try another example. Find the length of the curve given by y equals x cubed over 6 plus 1 over 2x on the interval 1/2 to 2. So again, this is y in terms of x, so I'm going to use a dx integral. And my arc length formula is the integral from a to b of the square root of 1 plus f prime of x squared dx. So we need to know what f prime of x is. Now, in order to do that, I'm going to rewrite this function just slightly first. Let me take that 6 and put it out front, and let me take this 1 over 2x and rewrite it as 1/2 x to the -1, just to make these power rules so that when I go to find f prime of x, it's pretty easy to do. When I bring down my 3, 3 times 1/6 is a half, and I subtract 1 from the power, so this is a square. When I bring down my -1, this becomes a -1/2, and when I subtract 1 from the power, it becomes a -2. So there's my derivative. All of that is going to go right here. So this becomes the square root of 1 plus 1/2 x squared minus 1/2 x to the -2 squared dx, and then my bounds, since I'm on the interval 1/2 to 2, this is going to be from 1/2 to 2. Okay, so again, these arc length integrals, messy to start off with. You usually need to do a little bit of simplifying first before you can figure out how to integrate it. So what I'm going to do first is I'm going to square out this derivative, and I'm going to have to FOIL. So make sure you get a middle term when you do that. When you take 1/2 x squared minus 1/2 x to the -2 and you multiply it by itself, you're going to get a 1/2 x squared times a 1/2 x squared, which is a 1/4 x to the 4th. You're going to get a 1/2 times a -1/2, which is a -1/4, and you're going to get an x squared times an x to the -2. When you add those powers, 2 plus -2 is 0, and x to the 0 is just a 1. So you're going to get a 1/2 x squared times a -1/2 x to the -2, and that's just a -4th. And you're going to get another one of those in the middle here. So the middle term is actually 2 times this negative 1/4, which is minus 1/2. Then on the end, we're going to get a negative 1/2 times a negative 1/2, which is a positive 1/4, and an x to the negative 2 times an x to the negative 2 is an x to the negative 4. So this is what it looks like. There's my 3 terms from my FOIL. Now the 1 and the minus 1/2 are like terms, so let's go ahead and combine them. I'm going to put this 1/4 x to the 4th in front. 1 minus 1/2 is positive 1/2, plus that 1/4 x to the negative 4. Now that looks very similar to what we got when we FOILed out this quantity squared. The only difference between these 3 terms and these 3 terms is that middle sign is opposite. So that means we get lucky here. These 3 terms that I have right here factor back into a perfect square. You need a 1/2 x squared in front to get that 1/4 x to the 4th. You need a 1/2 x to the negative 2 on the end to get that 1/4 x to the negative 4. And you need a plus in the middle to get that 1/4 plus 1/4, which is 1/2. So it looks just like this, but with a plus sign instead of a minus sign. Now the good news is, since that's a perfect square, it's going to cancel out that square root. So we lose the square root completely, which gives us 2 terms which we can integrate pretty easily. So I'm going to leave the 1/2 out front, and x squared becomes x cubed over 3. So this is x cubed over 6. And then this 1/2 stays put. When I add 1 to this power, negative 2 plus 1 is negative 1. So when I divide by that negative 1, this becomes a minus 1 over 2. And then I'm going to move that x to the negative 1 down to the bottom. And now I'm ready to plug in my bounds. So when I plug in 2 cubed is 8. So this is 8/6 minus 1/4. And when I plug in a half cubed is an 1/8 over 6. Minus 2 times a half is 1, so this is just 1 over 1. And then you can combine your fractions, get a common denominator. So we end up with 33 over 16 after that common denominator and simplifying. Okay? All right, let's try one more here. We want to find the length of the curve given by x equals y to the 4th over 16 plus 1 over 2y squared from 9/8 comma negative 2 to 9/16 comma negative 1. So this time my function is x in terms of y. So that means we're going to need to use that arc length formula in terms of y. So we're going to use a dy integral. So this is going to be the integral from c to d of the square root of 1 plus f prime of y squared dy. So let's find out what our f prime is going to be. Again, I'm going to do a little bit of rewriting on this function first. I'm going to make this a 1/16 x to the 4th plus a 1/2 y to the negative 2. Whoops, this should be a y to the 4th, not an x to the 4th. So when I go to find my f prime here, bringing down the 4 times 1/16 is 1/4 y cubed. Bringing down my negative 2 times that 1/2 makes it a minus 1 y to the negative 3. So we're ready to plug in. Our bounds for y are negative 2 to negative 1. And then we have the square root here of 1 plus this whole derivative, quantity squared dy. So just like in the last example, we're going to want to FOIL this out first. So if we look at 1/4 y cubed minus y to the negative 3 times 1/4 y cubed minus y to the negative 3, we're going to get in the front here a 1/16 y to the 6th. In the middle, we're going to get a minus 1/4 y to the negative 3 times y to the positive 3 is y to the 0, which is a 1, times that 1/4 out front, so the y's cancel out. And then for my other middle term, I get another 1/4 times a minus 1, and the y's cancel out again. And then on the end, we're going to get a minus times a minus is a plus. And when I add those powers, this is a y to the negative 6. So this is 1/16 y to the 6 minus a half plus y to the negative 6. So let's plug that in. We get square root of 1 plus these three terms. And again, we have some like terms. This 1 and this minus a half are like terms. So when I add those, I'm going to have that 1/16 y to the 6 out front. A 1 minus a half is a positive 1/2, and then I have that plus y to the negative 6 out front. And again, these three terms look just like these three, except the middle term has a different sign. So if I make these middle signs here be the opposites, this is going to factor back again. So it's very, very similar to the last example. These three terms factor into 1/4 y cubed in the front. Oops, let's just write it once here. And then a y to the negative 3 on the end, and I want a plus in the middle, so I need a plus inside here, and that quantity squared, FOILed out, gives me these three terms. Now there's one catch to this problem that's a little different than the last one. On the last one, we just said that the square and the square root are going to cancel each other out, and that is going to happen here with a slight technicality. Technically, the square root of y squared is not just y, it's really the absolute value of y. Now, I was a little bit lazy about that on the last example, but the reason I could get away with it in the last example was because my bounds were positive. So what I was plugging in for these x's were positive values, so I knew I would get a positive answer back again. That's not the case on this problem. Here my bounds are negative y values. So if I plug in a negative 2 and a negative 1, I'm going to potentially get negative answers, and we don't want to get a negative arc length. Arc length is a distance, and its distance should be positive. So technically I need absolute values here. Now the way to get around that is to basically take the absolute value of the whole answer at the very end. So I am going to cancel out my square root, and I'm going to use my bounds just like I normally would, but I'm going to make sure that I take the absolute value of my final answer to turn it into a positive distance. So let's proceed by integrating each of these. The 1/4 stays put, and y cubed becomes y to the 4th over 4, so this is going to become y to the 4th over 16. And then if I take the integral of a y to the negative 3, adding 1 to that gives me a negative 2 over a negative 2. So I'm going to pull that minus out front. I'm going to leave the 2 in the bottom, and I'm going to put that y squared down there as well, and I'm left with a 1 on top. And now I'm going to plug in my bounds. If I plug in a negative 1 and I raise it to a 4th power, that becomes a positive 1 over 16. And a negative 1 squared becomes positive, so this is minus a half. When I plug in negative 2, again it's going to become positive. 4 times 4 is 16, and 16 over 16 is a 1. And 2 squared is 4, 4 times 2 is 8, so this will be a 1/8. So I have a 1/16, a minus 1/2. When I distribute my negative, I get a minus 1 and a plus 1/8. And I'm going to show you what we get here with our common denominators. Let's just make everything have a denominator of 16. This is a 1. 1/2 is 8/16. 1 is 16/16. And 1/8 is 2/16. So 1 minus 8 is negative 7. Negative 7 minus 16 is negative 23. Negative 23 plus 1 is negative 21/16. Because that's negative, remember we said we don't want a negative distance, then we can take our absolute values at the end and get our final answer, 21/16. If you prefer, you could get a decimal here, and that would be 1.3125. Okay? Remember that you can also use that function integrate command on your calculator. It's under the math button number 9, and you can use that to double check your answers and make sure that you're getting the right solutions as well. Okay, so arc lengths, the integral of the square root of 1 plus f prime quantity squared. Okay? Now we're going to expand on that a little bit by talking about surface area of revolution. Now we've talked about volumes of revolution by taking a bounded region and rotating it around an axis of revolution and then finding the volume of that new picture that you create. So what we're going to do now is we're going to find not the volume of that region, but this time the surface area of that region. So the amount of area it would take to wrap around that object. So definition of surface area of revolution. The surface area of revolution is the surface area created when the graph of a continuous function is revolved about a line. So here would be an example of a region that we would have gotten by rotating this sort of curvy picture here in quadrant 1 around the x-axis. So you almost get this sort of vase shape to it. Now we know how to find the volume of that already. You could use the disk method to do that. But what we're going to do differently is instead of finding the volume of it, we're going to find its surface area. So imagine painting the outside of this vase. How much paint would you need? That's exactly what the surface area is measuring. So to do this, we're going to do something similar that we did for volumes, and that is to look at sort of a little cross-sectional cut here, which is going to have this shape of a disc initially. It looks like a disc, but if you look at it and you sort of expand it a little bit into a bigger picture, it's not actually a disc because this is curving along the endpoints. It's actually going to have the shape of what we call the frustum of a cone. So it's like a disc, except that the edges here are not flat. They're actually angled either up or down depending on where you are on this curve. So for example, if I look at this one over here, this is going to be going up and down like this, so you're going to have this kind of shape over here. But if I look at one over here, then I go down and down, so this would be more like a frustum that would look like that. That little piece blown up turns into that shape. So what would be the surface area of this kind of shape? Well, it turns out that the surface area of the frustum of a cone is given by 2 pi r times the L, where L is the length of this line segment going across here, this arc length, and r is actually a function of the two different radii here. It's actually the average of the left radius and the right radius. Okay, so using that idea, we can say that the amount of surface area in just this little slice is given by 2 pi r times the change in that arc length, that change in that length. And when you take a limit and make these slices get smaller and skinnier, then this turns into an integral. And the surface area integral that it turns into is 2 pi times the integral of r of x, so this radius is going to be a function of either x or y, times your arc length. And this is the same arc length formula that we just talked about, the square root of 1 plus f prime of x quantity squared, or if you're doing y's, the square root of 1 plus f prime of y quantity squared dy. So you get two different versions of this surface area formula. And it's basically derived from that 2 pi rl formula for the surface area of a frustum of a cone. So these are the formulas that you want to memorize. Surface area is equal to 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x quantity squared, where r of x is the distance between the curve and the axis of revolution. That same idea of radius that we talk about when we're doing volumes of revolution in the disk method or the washer method. S equals 2 pi r times the integral from c to d of r of y square root of 1 plus f prime of y quantity squared dy is the alternative version using y's. And again, r of y would just be the distance between the curve and the axis of revolution. The unique thing about this surface area formula is you can actually use either version, and it's independent of your axis of revolution. If you remember from our disks and washers, we always took our disks and washers perpendicular to the axis of revolution, and for shells we always took our shells parallel to the axis of revolution. For surface areas, it doesn't matter. It doesn't matter which way your axis goes. You can use either a dx or a dy integral. And usually what I recommend is that if your function is invertible, which means it's easy to go back and forth between x and y and solve for x or solve for y, then it doesn't matter. Do whichever one of these is easier. If your function is not invertible, in other words, it's difficult to solve for x in terms of y or y in terms of x, then use the variable that's in the original formula so that you don't have to invert it. Okay, let me give you some examples. So, suppose that you want to find the surface area of revolution formed by revolving the graph of y equals x cubed from 1, 1 to 2, 8 about the x-axis. Okay, so let's draw this picture first, and then we'll talk about which version of our formula we're going to use. So x cubed looks like this, and we want it from 1, 1 up to 2, 8. So I'm going to get this piece out of the way. We don't need that. And we're going to rotate this around the x-axis. So when I do the mirror image down here, it's going to look something like this. Okay? Now, my first instinct, just from experience with our volumes, is to usually just draw in your disk vertically like this. And you're going to want to do that vertical disk no matter what, because your disk is going to follow the direction of that axis of revolution. So you always want your sort of disk shape here to be in that circular shape around that axis of revolution, so it's going to be perpendicular to that axis of revolution. The choices, though, that you have is how you define your radius function and what variable you choose to use. Now, y equals x cubed is what I would consider an invertible function. It's easy to solve for x in terms of y by just taking a cube root. So we can really do this problem either way, and I'm going to show you both options here. So let's start by doing it and labeling how we normally would for volumes of revolution. If I want to know my radius function, because remember for surface area, it's 2 pi times your radius function, which is either r of x or r of y, times the square root of 1 plus f prime of x quantity squared, or square root of 1 plus f prime of y quantity squared. So this is our basic formula that we want to use, either one of these. So if I want to find this radius function first, which is where you want to start, we need to know the center point of our circle and the top point of our circle. And we want to find these 2 points so that we can figure out what that distance r is going to be. So option number 1, to do it consistently how we do volumes using the disk method, we would say that both of these 2 points share the same x coordinate. The bottom point is on the x-axis, so its y value is 0, and the top point is on the curve, so its y value is the same as this formula, x cubed. So we would say, using disks here, that this radius function would be the top y value minus the bottom y value, which makes this radius function just x cubed. So that means I want to use x's if I'm going to do this problem this particular way. So my surface area would become 2 pi times the integral of my radius function, which is x cubed, times the square root of 1 plus, and now we need to know f prime of x. Well, if my function is x cubed, then f prime of x is just 3x squared. So that's going to go here, and I want to square that derivative. Since I'm using x's, my bounds for x's are from 1 to 2. So that would be my surface area integral using x's. Now let's go ahead and finish solving this, and then I'll show you how you could do the same problem using a dy integral as well. So we get that x cubed out front, and 3x squared quantity squared becomes 9x to the fourth. Now this is actually good for us because if you think of this as a pattern recognition problem, your outermost function is this square root. Your innermost function is this 1 plus 9x to the fourth. We'll call that g. And the derivative of that wants to be 36x cubed. And I thankfully have the x cubed already there. I'm just missing the 36. And then I would have the right g prime. So we can counterbalance by our 36 underneath and out front. So this becomes pi over 18. And since I have all three pieces that are required for pattern recognition, then to integrate using pattern recognition, you only integrate the outermost function, which is this 1/2 power. So what do you get when you integrate a 1/2? Well, when you add a 1 to 1/2, you get 3/2 with a 2/3 out front. And what's inside stays the same. So this becomes pi over 27, and then 1 plus 9x to the fourth raised to the 3/2, and I'm plugging in my 1 and my 2 into that. So we get pi over 27, plugging in a 2 to the fourth is 16, and then we're going to need to multiply by that 9 and raise all of that to the 3/2, and then we're going to subtract from that. When I plug in 1 to the fourth is still 1, and we'll get a 1 plus 9 raised to the 3/2. And this isn't going to come out really nice. These are not going to be nice values that simplify, so I'm just going to go ahead and tell you the decimal value here. Once you punch it into your calculator, it's about 199.48. Okay? All right, now as an alternative, just to show you that it's possible here, I'm going to do the same problem, but I'm going to do it using y's. So we're going to still take our region, which is that cubic function from 1 to 2. We're still rotating it around the x-axis. You still want to have that circle going perpendicular to that axis of revolution, but here's the change. Instead of saying that these 2 points share the same x value, which they still do, what I'm really interested in are the y's, because it's the y's that are going to tell me this height difference here. So what I'm going to say is this bottom point still has a y coordinate of 0, but let's just say that this top point has a generic y value on top. And I'm not even going to put in that equation of that curve here. I'm just going to call it just some generic point on the curve, x comma y. So then this radius function would be this top point minus this bottom point, which would be y minus 0, or just a y. So in this problem, this radius function is determined by the y coordinate of that top point. So if I use my radius as y instead, then this surface area formula becomes 2 pi times the radius function, which now I'm just using y, times the square root of 1 plus f prime of y quantity squared. So here's where we have to use that invertible function idea. Remember, our function y was x cubed. Now in order to find f prime of y, I need to solve this for x first. So if I take a cube root of both sides, a cube root is the same as a 1/3 power, then the derivative of this in terms of y is going to be the derivative of y to the 1/3, which is just 1/3 y to the negative 2/3. So that is what I would use right here for my f prime. And I want to square that, and this is going to be a dy. So if you use for your radius function the y variable, then you need to use the derivative of this function in terms of y's as well. Everything in here should be y's, not x's. And that goes for the bounds as well. Remember, our points were 1, 1 to 2, 8. So the y's go from 1 up to 8. So those are going to be my bounds here as well. So this becomes 2 pi times the integral from 1 to 8 of y times the square root of 1 plus 1/3 squared becomes 1/9, and negative 2/3 times 2 makes this a y to the negative 4/3 dy. Now this is doable, it's just messy, okay? This would have to be changed into, on the bottom here, getting a common denominator. Whoops, let me rewrite it this way. A 9y to the 4/3. 1 is the same as 9y to the 4/3 over 9y to the 4/3. And then on top here would just be this 1 because I've moved both of these down to the bottom. Square root of 9y to the 4/3, that does reduce. 3y to the 2/3. And then I can reduce my y's out front here. This is like a y to the 1. So a y to the 1 minus y to the 2/3, because when you are dividing you subtract the powers. This becomes a y to the 1/3. I'm going to go ahead and take that 3 and pull it out. So here's what we have. Still looks pretty messy. This is doable though, because we can do a little U-substitution again. If I let my u be 9y to the 4/3 plus 1, then du is going to be 9 times 4/3, which is 36/3, y to the 1/3 dy, and 36/3 is just 12. If I divide that 12 over to the other side, then that leaves me just y to the 1/3 dy, which is exactly this and this together. So this becomes 2 pi over 3 times, all of this is square root of u, and the y to the 1/3 dy becomes my du over 12. So this is 2 pi, I'll just write it as 2 pi over 3 times 12 is 36, and the integral of square root of u is, that's a u to the 1/2, so when I add 1 it becomes u to the 3/2 times 2/3. So we're going to get pi over 27, and if I resubstitute back in terms of u, this is 9y to the 4/3 plus 1 raised to the 3/2, and then I'm ready to plug in my 1 and my 8. And it's going to give you the same answer that we got before, 199.48. So, surface areas of revolution. As you can see, it is possible to do this using y variables or x's, but as you can probably see from the work, that usually one or the other is going to be a little bit easier to actually integrate. So sometimes if you start out with one particular method and you end up with an integral that looks pretty messy, then I would recommend trying the other option, letting your radius function be something else instead, and hopefully that second option will give you a much simpler integral to solve and would take less time to do. Okay, most of the time you can let that radius just be an x or a y, but as you saw from this example, letting that radius be x cubed actually gave us a little easier problem and a little simpler integral with less work. Let's try another example. Find the surface area of the region formed by revolving the graph of f of x equals x squared on the interval 0 to square root of 2 about the y-axis. Okay, let's start by drawing our region. So we want to take the curve f of x equals x squared, and we're rotating this around the y-axis. So when I rotate that curve around, it's going to look like this, like a cup shape almost. And we're going from 0 to square root of 2. And we want to find the area of this surface formed by revolving this around the y-axis. So the surface area of that cup shape. Okay, so to use our formula correctly, we want to draw in that slice. We're going to take our slice perpendicular to the axis of revolution, So we get that circular shape, and we want this radius going across here. So your two options, if we do this like we would do it for volumes of disks, we would say that these 2 points are at the same height, so they share the same y value. The center point is on the y-axis, so its x value is 0, and the rim point is on the curve, which is f of x equals to x squared, or y equals to x squared. Now I'm using y's here, so I need to know what this x value is in terms of y. Luckily this function is invertible, so I can solve it for x by just taking a square root. So the x value of this point would be square root of y. So my radius function would be this right point minus this left point, or square root of y minus 0. Okay, now that's option 1. Really quickly, let's see option 2. Same region, same disk shape, everything's the same, but instead of looking at the entire coordinates of both of these points, the only coordinates that matter are the x's, because this is a horizontal distance going across. We know the x value of the center point is 0 because it's on that y-axis. And let's just call this rim point a generic x comma y. So if I think of it that way, then my radius will be this x point here minus this x point here, so my radius would be x. Now this saves you a little bit of time because you didn't have to invert your function at all. So our formula at this point would then be 2 pi times my radius function times the square root of 1 plus f prime of x quantity squared dx. And up here, my surface area formula would be 2 pi times my radius function times 1 plus f prime of y quantity squared dy. So now the difference is going to be, we know what our r function is. In this case it was square root of y, and in this case it's just x. The next piece that's going to vary is what this derivative is going to be. So in this problem up here, you need to find out what the derivative of this function is in terms of y. So that's where you're going to need to use that invertible function again. Since we know after inverting it that x is square root of y, which is the same as y to the 1/2, then that means f prime of y is 1/2 y to the negative 1/2. So that's what I would use inside of my square root. And to me already this looks pretty messy. The other issue here would be the bounds, right? We need y bounds. So we know the bottom bound is 0. We need to know what the top bound is. So if my x bound here is square root of 2, what height does that go to on this curve? Well, if x is root 2, then root 2 squared just becomes 2. So this is at a height of 2, so my bounds would be from 0 to 2. So this is option number 1. And just looking at that, that looks like a much messier integral to solve and much more work. So let's continue with this option down here and see if this gets any better. So let's find f prime of x for this one. Here our function doesn't require any inversion because I can just take the derivative right away. Derivative of x squared would be 2x. So this is 1 plus 2x quantity squared dx, and my bounds would just be that 0 to that root 2. So not only was it simpler to set up, it's actually simpler looking to solve, because this is going to become 2 pi times the integral from 0 to root 2 of x times 1 plus 4x squared, and that is just pattern recognition. My outer function is the square root. My inner function is this 1 plus 4x squared. The derivative of that wants to be an 8x. I have the x, so put in the 8, and now I have the right g prime, counterbalanced by dividing by 8. So when I integrate this, this 2 pi over 8 becomes pi over 4, and the only piece of this that I need to integrate is that outer function, which is a 1/2, When you add 1 to 1/2, it becomes 3/2 times 2/3, and what's inside stays inside. So this becomes pi over 6 times 1 plus 4x squared to the 3/2, and I'm plugging in 0 and square root of 2. So we get pi over 6 out front. When I plug in root 2 and I square it, it becomes a 2. 2 times 4 is 8. 8 plus 1 is 9. So this is 9 to the 3/2, which actually reduces because the square root of 9 is 3 and 3 cubed is 27. If I plug in 0, this whole term becomes a 0, but we still have to add 1 to that. So that's going to give me a 1 to the 3/2, and we're subtracting that upper and lower bound. So this is just 27 minus 1, which is 26, times that pi over 6, and if I divide by some 2's, I get 13 pi over 3. Now you would get the same exact answer if you finish solving this one, but I personally think that this was harder to set up and harder to finish solving. So that's why I would have chosen this option instead, where I let r just be x, because it gives me an easier integral to solve. So that's the flexibility of that surface area formula, and the fact that you can use either x's or y's. Use whichever one is going to give you an integral that's easier to solve by hand. Okay, our last example here. Derive the formula for the surface area of a cone. So to create our cone, I'm going to take the line segment between the points r, 0 on the x-axis and 0, h on the y-axis. That way my cone has height h and a radius of r. And I'm going to rotate that line segment around the y-axis so that we get this cone shape. Now going perpendicular to that axis of revolution, it's going to give me that circular shape right there. So we need to know what this radius is going across. Now you have your two choices again, so I'm going to show you how to set up both of these two integrals, but we'll only solve one of them. Okay? So option number 1 is to recognize that these 2 points are at the same height, so they both share the same y value. The center point has an x value of 0, and the right point over here on the edge is determined by this line. So we need to do a little bit of work here to figure out what the equation of this line is. So let's do that over here. If you think about the equation of a line as y equals mx plus b, what's the slope of this line? Well, if I start up here, I have to go down h and over r. So that would be a slope of negative h over r times our x. And what's the b? Where does this line segment cross the y-axis? It crosses at h. So b is h. Now, unfortunately, over here in my ordered pair, I need to know what this x value is in terms of y. So I would need to invert this and solve it for x in terms of y. So let's go ahead and do that. I'm going to go ahead and add the h over r x to the left side, and I'm going to subtract the y over to the right side, and then I'm going to multiply by the reciprocal r over h so that this cancels out. Now r over h times h is just r minus r over h times y. So this is what x is in terms of y. So that would go right here. So my radius function in terms of y is going to be this right x value minus this left x value, which is just this formula that we came up with over here for what x was. So my surface area is going to be 2 pi times this radius function, we're using y's, times the square root of f prime of y quantity squared dy. So this is going to become 2 pi times all of this times the square root of 1 plus, now we need to figure out what f prime of y is. So again, that requires inverting it and putting this line segment in terms of y's, which we already did right here. So the derivative of this in terms of y would be what? Well, the derivative of r is 0 because r is a constant in this problem. And the derivative of minus r over h times y is just that coefficient minus r over h. The derivative of y goes to 1. So our derivative is going to be negative r over h, and we want to square that. And then what are my bounds for y? Well, I start at 0 and I go up to h. So this is going to be from 0 to h. Okay? So that's what my dy integral would look like if we go ahead and square out here a little bit. This would become 1 plus r squared over h squared dy. Now this is doable, it's just going to take a little bit of work to finish it out. Okay? Before we get to the actual solving, let's talk about what the alternative version of this would look like. So let's come down here, and if we look at our picture again, when I rotate this around, here's my cone, and I'm still going to take that circle perpendicular to the axis of revolution, but this time when I come up with my radius function, it's this horizontal distance between these 2 points. So if I look at this point on the line and just call that a generic x comma y, then this point over here has its x value of 0, so the radius is going to be determined by this generic x minus this 0, so the radius function is just x. Okay, so our surface area formula using x's is 2 pi times the integral of our radius function in terms of x times the square root of 1 plus f prime of x squared dx. So this is going to become 2 pi times the integral of just an x, and now we have to figure out what f prime of x is going to be. So how do we do that? Well, remember the equation of this line. It was our slope, which was negative h over r times x, plus our b, which was h. So the derivative of this is just that slope, negative h over r. So that's what I would use right here. And my bounds for x are from 0 to r. So this is what the integral would look like using x's. This is what the integral would look like using y's. Which one looks easier? Well, they're pretty similar, but I personally think this bottom one looks a little bit simpler because my radius function is simpler. It's not as complicated as all of this. So in terms of which one am I going to solve, I'm going to solve the bottom one. So let's see what this gives me. I get this x, and if I square here, I'm going to get 1 plus h squared over r squared. Let's get a common denominator inside of that square root. My denominator would be r squared, so 1 is r squared over r squared plus this h squared that I had on top before. And that r squared on the bottom actually reduces, because it's a nice perfect square, into just an r. And all these things are positive, so I don't need to worry about any absolute values. Now, here's the thing to notice that's going to make your life easier. Remember, the radius r and the height h, those are constants. So all of this is just one big constant which I can pull outside of my integral. There's no x inside of there at all. So I can pull all of this out. And so the only piece of this that I'm actually integrating is that x from that radius function. And what's the integral of x? Well, that's just going to become x squared over 2, and my bounds are 0 to r. So if I plug in r, I'm going to get an r squared over 2. If I plug in 0, I'm going to get 0. So if I multiply, one of these r's cancels out and the 2's cancels out. So we're left with our pi, this r, and this square root of r squared plus h squared. So that's the formula for surface area of a cone. And sometimes they'll use a new symbol. They'll let L be the square root of r squared plus h squared. Notice what that is on this picture. If this is r and this is h, r squared plus h squared, the square root of that is this hypotenuse. That's Pythagorean theorem. So L is the length of this hypotenuse, which is sometimes called the slant height. So sometimes this surface area formula is written as pi r L, where L is that slant distance right there. Okay, so there's the derivation of the surface area formula for a cone. Alright, that concludes our video lecture on arc length and surfaces of revolution. Good luck!